Hello students, in this video we'll discuss two special classes of unitary matrices, householder transformations and Given's rotations. Let's be given a complex vector, W, which resides in Cn. Define a matrix, let's call this matrix U that depends on W, by the identity minus twice W star W inverse W W star. And those are all vectors, of course, like that. And then this matrix UW is called a householder matrix. Okay, and over here we're assuming that this vector W is not equal to 0, right? So here, the vector W is not the 0 vector, and that means that this number over here, W star W, is just the length of W quantity squared, like that. Okay, excellent. And so let's talk about some basic properties of householder matrices. They're really important in numerical analysis, but there's a couple of elementary quantities we can figure out real fast. So let's do this. Properties of these householders is that if I look at, let's figure out which UW star is its complex conjugate, right? So it's going to be what? It's going to be identity minus twice W. I'm going to suppress the vector notation over here and just leave this W. Twice W star W inverse W W star. That's a projection onto W, obviously, right? And then we're going to star this thing over here. And by the linearity of star, this is just identity star minus twice W. And of course, those come out as complex conjugates, right? But that's just a real number, right? So I don't need to conjugate a real number. So this is going to be W star W inverse. Technically, this whole thing is conjugate, but that's a real number, right? And then I'm going to have W star star W star. And of course, what will this simplify to? This is just going to simplify to the identity because that's self-involutory minus 2 W star W inverse. That's real. And then W W star. And that's just going to be UW, and that says that UW star, that says that UW star is UW. So in other words, this is a Hermitian operator. So hence, UW is a Hermitian operator. Okay, and that means it has real eigenvalues, right? So in other words, the eigenvalues are real. So in other words, the spectrum of UW is a subset of the real line, right? Okay, that's a very, very useful thing. The next property we're going to prove, property 2, is that it's self-involutory. In other words, what we want to do is we want to look at UW inverse. Okay. We claim that UW inverse is equal to just UW. Of course, how can we see something like this, right? Well, what can we do? Let's prove it. So here's the proof of this fact. Proof. If I look up the identity minus 2 W star W inverse in the direction of W W star, right? And I hit that with the identity minus 2 W star W inverse W W star. What's going to happen over here? So let's distribute this out and see what we get. We're going to have the identity over here. Then these terms will just multiply with the identity. So I'm going to get a total of 4 of these things, W star W inverse W W star, like that. And then what happens when I do these two operators at the very, very end over here? What are we going to have, right? We're going to have these things over here. We're going to have a total of 4. And then I'm going to have a W star W inverse with 2 of them, right? And then over here, what are we going to have? We're going to have the factor of W star W and then W W star, like that. This inner term over here is exactly equal to what? That is exactly equal to identity minus 4 W star W inverse, and then W W star. And then over here, that we're going to cancel out one of those because that's exactly one of these things over here. So that's going to be plus a factor of 4. And then what? And then W star W to the power -1. And then W W star. We see these 4s with these are exactly the same term over here. So this is just the identity operator, right? And of course, what I've just shown over here is I've just done, this is just UW over here, and this is just UW over here. So in other words, UW, 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 and then UW, the UW over here, UW is the identity set for the self-inverse. And of course, from this, what can we conclude? We can conclude, therefore, that since this is since UW is UW star, we can say that UW inverse is equal to UW star, right? So we have this property over here of these householder transformations. Now, the last thing to understand with these householder transformations is the following. Well, there are many things to understand about them, but in terms of the basic properties, next property is the following. The eigenvalues of this thing are either plus or minus 1. So in other words, not only are they an R, but they're only plus minus 1. Okay, even better, right? Of course, we know that's actually sort of fairly easy to prove. Once I prove that it's a Hermitian operator, and we know that it's actually going to also be normal for this because it's going to commute with its adjoint. We know it's going to be on the unit circle and on the real line. They only intersect the plus minus 1. So how do we see that, right? So in other words, what can happen in these transformations? So what we're going to do is we're going to suppose, let's consider the space vector W perp is the orthogonal complement. This is just a span of the vector W perpendicular, right? This thing is an n-1 complex dimensional thing. Okay? And let's see what happens when I plug in anything that's perpendicular to W into there, right? So suppose, so let's let X be in the W perp, right? And let's look at UW of X. What's that going to be? That's going to be just going to be, I'm going to plug it into the identities. That's just going to be an X, right? And then minus 2W star W inverse, and then W star hit with X over here, right? But when I hit W star with X, I get 0 because it's perpendicular to these things. That's just the dot product over here. So this is just going to be equal to 0. This term is just gone. That's just 0. That's just X, right? So anything in the orthogonal complement of W is going to give us what? It's going to give us an eigenvalue of 1, right? So this says that X is an eigenvector with lambda equals 1. So 1's an eigenvalue over here with this eigenvector that's everything in the orthogonal complement. And then what's the other thing we can say? The other thing we can say is that if we plug in W to this thing, that's the other n one-dimensional complex thing, then UW of W is going to be what? It's going to be W minus what? Minus 2W, which is just negative W. And that says that lambda is equal to negative 1, right? So lambda is equal to negative 1, or lambda is equal to 1. So the spectrum of this thing is just 1 or negative 1. Moreover, I know the dimension of the eigenspace that corresponds to W is just going to be one-dimensional, one complex dimensional. And so we get a bonus from this, namely that the determinant of these householder matrices are just going to be equal to negative 1, right? So by carefully examining what we get when we plug in the W vector into the householder matrix, and when we plug in anything in the orthogonal complement, we're able to determine what the spectrum of that matrix is going to be, in addition to understanding its determinant structure and also the geometry, right? So there's a reflective geometry over here. So in other words, it's a complete improper rotation in the complex plane. And so we'll study how these householder matrices can be used to help us gain tridiagonal structure and numerical schemes in further videos. Thank you very much.